Hello and welcome to my YouTube channel, Scholars and Curious. And physics is obviously for curious ones. This is Monica Srivastava. I have again an interesting video for you guys. As you can see the starting page, which is saying we are going to solve TIFR previous year questions today. Basically of solid state physics, because we were reading solid state physics from last 2 to 2.5 months. That is why we are continuing with it, and we will solve some questions from TIFR papers. It is a very important exams, and the level of questions is quite hard, we can say, harder than the net and get papers. So here we start with the question number 1. What is this question saying? Let's read out the question first and then I'll tell you how to solve this question. This question is basically from TIFR 2012. So the question is saying a monochromatic beam of X-rays with wavelength lambda is incident at an angle theta on a crystal with lattice spacings A and B as sketched in the figure below. And you can see the figure. So it is the figure given, which is saying that this distance is A, this is B, monochromatic beam of X-rays coming, the wavelength of this beam is lambda and the incident angle is theta. Okay. Next is a condition for there to be a maximum in the diffracted X-ray intensity is, and there are 4 options. We have to find out the suitable condition by which we can get the diffracted X-rays maximum intensity. The condition to get maximum X-ray diffracted intensity. So how to solve this type of question? Let me tell you, and this is the answer. So let us make that diagram again. This is the diagram. This is your incident ray, and this is diffracted one. This is your incident ray, and this is diffracted or scattered ones. So if this one is theta, then this angle will also be theta, and this angle, this one inside it, this angle, it will also be theta. So this will be your A cos theta. Again, this will be your A cos theta. So let's solve this question now. So the path difference is usually the path traveled of the ray inside the material or the sample. So A cos theta plus A cos theta equals to n lambda, which will be the multiple of the wavelength of incident beam. So A cos theta plus A cos theta equals to n lambda. So we can say 2A cos theta equals to n lambda. So let's check the option. I think amongst these 4, this option A is the correct one. 2A cos theta equals to lambda. So here they are putting n equals to 1. So we are getting the condition, the suitable condition for maximum diffracted X-ray intensity is 2A cos theta equals to lambda. Moving ahead. Second question. Suppose the energy band diagram of a certain pure crystalline solid is as shown in the figure below. And you can see the figure where the energy E varies with crystal momentum K. So the dispersion relation is given. So the dispersion relation is E is proportional to K square. This is your conduction band. This is your valence band. And where K they are denoting is crystal momentum. So the question is, at finite temperature, the bottom of the conduction band is partially filled with electrons and the top of the valence band is partially filled with holes. If an electric field is applied to this solid, both electron and hole will start moving. If the time between collision is same for both, then, and there are 4 options. So what are they saying? That bottom of conduction band, this area, is filled with electrons. So here are some electrons. And the top of the valence band, there are holes. So by H we are denoting the holes. So here are some holes. And they are moving because some holes will go here, some electrons will come here, and so they are moving, and the time of collision of them is like same for both electron and hole, then what will be the correct one? Option A is saying E and H will move with same speed in opposite direction. Option B is H will on an average achieve higher speed than E. Option C is E will on an average achieve higher speed than H, and D is E and H will recombine and after a while there will be no flow of charges. So we have studied the theory of the band theory. We have studied that earlier. So the band theory says that there are some bands like valence band, conduction band and insulation band, and the movement of electrons and holes decide what type of material that is. The energy band gap between the band decide what type of material that is. So we know that the speed of moving of electron and hole both are same. Like if we are considering crystal momentum also, then also the hole will gain the same speed as the speed of electron, which is the velocity of light, c, 3 into 10 to the power 8 meter per second. So we can only consider their masses. Okay, you know the mass of electron, and let's check the answer. So we don't know what type of material it is. It is silicon or germanium. We just know that it is a semiconductor because they are talking about electron or holes. So we can't compare it by drift velocity and mobility and their moment. So yes, but we can just conclude that hole will move with higher speed as compared to electrons. Because why? Because holes have rest mass 0. And electrons have some mass, at least we know 9.1 into 10 to the power minus 31 kgs. That is the mass of electron. But holes have rest mass 0. That is why holes will move with higher speed. So the correct option will be B. H will on an average achieve higher speed than E, electrons. Okay. Question third. Metallic copper is known to form cubic crystals and the lattice constant is measured from X-ray diffraction studies to be about 0.36 nanometer if the specific gravity of copper is 8.96 and its atomic weight is 63.5. One can conclude that it is an easy question. There are 5 options and you can easily find out the result. We have to conclude what type of crystal structure it is. They are talking about metallic copper. And we have to find out what type of crystal structure it is achieving, metallic copper is achieving. And they have given some mathematical data like the lattice constant is given here, the specific gravity is given here, atomic weight of copper is given here. So it is quite an easy question. And how to solve this? This is the approach. So atomic weight of copper is this much, 63.5. Mass of one copper atom, we can conclude the mass if we have given the weight now of any atom. So we have the mass of one copper atom, this 1.054 into 10 to the power minus 22 gram. Volume of unit cell. What is volume? Volume is the cube of one side, obviously. Because it is a cubic type of structure, but we don't know what type of cubic, FCC, BCC, SC or what type of. So we will just do the cube of this one. We are getting this, and mass of unit cell, we know how to calculate. Now, the number of copper atom in one unit cell, the formula is mass of one unit cell upon mass of one copper atom. So this is your mass of one unit cell, we have calculated, and this is your mass of one copper atom. Again we have calculated. Just do it. We are approximately getting number of copper atom in one unit cell is 4, approximately 4. Now, by this we can conclude that it is FCC cell. Why? Because in a FCC structure, there are number of atoms in one unit cell is used to be 4. In BCC, the number is 2. In FCC, in simple cubic SC, the number is 1. So the correct answer is E. The crystals are of FCC type. This question was from TIFR 2012. Moving ahead, question number 4. See, this question is a tricky question. let's read out it first. A parallel beam of light of wavelength lambda is incident on a transmission grating with groove spacing d. This is the spacing. At an angle theta I, incidence angle, as shown in figure on the left. The plane of incidence is normal to the grooves. You can see this one and this one, both are normal to each other. After diffraction, the transmitted beam is seen to be at an angle alpha. Here, this is alpha, relative to the normal. Which of the following conditions must be satisfied for this to happen? We have to choose one appropriate condition, and this question is from Tifr 2013. So there are many approaches to solve this question. We are solve this question by using Bragg's law and Davison-Germer's experiment. So how we will solve this? The approach is this one. First of all, we know the Bragg's law. They are talking about grating spectrum. So how from here to here we can calculate, we can relate the grating spectrum and Bragg's law. You can see this. This is the procedure. So basically we are going to start with Bragg's law. You know that is 2d sin theta equals to n lambda. Now they have given the interplanar distance. The formula for the interplanar distance for the grating is d equals to a over under root l square plus m square plus n square. And from the diagram, this one is the right relation, 2 theta plus phi equals to n. And for these types of question, the simple approach will be this. You have to solve these type of questions by using this one, 2 theta plus phi equals to n, where theta you will get pi by 2 minus pi by 2. You will put in the Bragg's law instead of this theta, the value of theta in form of pi and phi, and thus you will get 2d cos phi by 2 equals to n lambda. Now we will include the Davison-Germer experiment. The Davison-Germer experiment was on the diffracted electrons, basically on, and they have used the nickel crystal. They have incident some electrons on the angle 50 degree, and the energies electron gained was 54 electron volt. You can see the Davison-Germer experiment. If you guys are unable, when we will start the series of quantum mechanics, I will tell you very briefly that what was that experiment. And then this is the overview of Davison-Germer experiment, and then we will include Bragg's law too, and thus we will get the appropriate condition, this one, d sin theta 1 plus sin alpha equals to n lambda. So the correct option we will get will be option number A. There are many approaches to solve these types of questions, but this approach I think is much suitable. Next question is, the magnetic susceptibility chi of three samples A, B and C is measured as a function of their absolute temperature T, leading to the graphs shown below. There are three graphs A, B and C. The graphs are between 1 upon chi, means the inverse of susceptibility and the temperature. So from these graphs we have to calculate the magnetic nature of these three samples A, B and C, and there are four options. A may be antiferromagnet, or A may be diamagnet, or A may be paramagnet, or A may be antiferromagnet. So let's start with this B. So first of all, what type of nature B will have? Let me tell you, the those substances which are paramagnets, now they for them temperature is directly proportional to 1 over susceptibility. Okay, if we are increasing the temperature, susceptibility decreases, magnetic susceptibility decreases for the paramagnets. So B will surely be a paramagnet. Now let's talk about diamagnets. So if between A and C anyone is diamagnet, let me tell you first that when we will increase the temperature, now the susceptibility of diamagnets is usually negative. So it goes on negative, and there is some dotted line here, not for sure probability. So between A and C no one is diamagnet, and by just viewing these four options we are getting if B is paramagnet, then either option B or option D may correct. So we know that A is not a diamagnet. That is why option D is the correct one. So yes, option D. And this question was from TIFR 2013. Question number 6. The sign of the majority charge carriers in a doped silicon crystal is to be determined experimentally. In addition to a voltage supply, the combination of instruments needed to perform the experiment is. See, all the answers may be correct. Like we can tune them and we can measure the voltage supply of the combination of, like, for any doped semiconducting crystal. But more appropriate answer we think is C. We can use pickup coil, voltmeter and ammeter. So yes. Question number 7. The figure below shows the Bragg diffraction pattern for X-rays of wavelength 1.54 angstrom incident on two crystalline silicon thin film sample A and B. The dashed line corresponds to a normal sample A and continuous line corresponds to another sample B, which is modified due to difference in growth conditions. These plots suggest that the modified sample B is. There are two sharp peaks we are getting with the experiment X-ray diffraction, Bragg diffraction pattern, and we are getting this type of pattern. So it is saying that there was a normal sample A and there is another sample B which is modified from A. Okay, there is a modified peak. Now what we have modified, like what we have done with this sample, that we are getting this type of spectra, not this. We are getting modified spectra, this one, this B1. So what we have done, either we have stressed it, like stressed the sample in all directions by 3%, or we have compressed it in all directions by 3%, or we have stressed in Z direction but compressed in X and Y direction, or we have compressed in Z direction or stressed out in X and Y directions. So just basically this is the question from XRD power pattern using Bragg diffraction, and this is a research problem, but it is a quite easy problem. The approach will be like, if any peak is modifying and in the option they are saying that they have stressed or compressed, that means there we are generating some strain, we are generating some disturbance. So if sample is stressed out or compressed out, the peak will be modified. Okay, so this is the Bragg's law, 2d sin theta equals to n lambda, and we can conclude d equals to n lambda upon sin theta. Now we can say that if we are increasing this theta, d is decreasing, and if we are decreasing this theta, d is increasing, because you can say d is inversely proportional to theta. So if we want to compress in z direction, what is z direction? This is given in this question. See here, this is your z direction. If you want to compress, like you are compressing this sample in this direction, you are compressing it, you are putting some pressure, you are compressing in z direction, then you are getting theta is decreasing and d is increasing. When d increases, okay, when d increases, then x and y will automatically stretch out. X and y will automatically stretch out. So the correct option will be option number D, compressed in z direction and possibly stretched out in x and y direction. Moving ahead, question number 8 is here. Which of the following graphs qualitatively describe the pressure of a gas of non-interacting fermion in thermal equilibrium at a constant volume as a function of temperature? So we have to figure out the appropriate graph for non-interacting fermions, and the graphs are between pressure and temperature. we have to figure out appropriate graph for non-interacting fermions. They are fermions. Let's take an example, electron. We are talking about electron. And electron is non-interacting and there is a thermal equilibrium. So, with these graphs, we can conclude that option number C will be the appropriate one, because for fermions at absolute temperature, energy is not equals to 0, even velocity is not equals to 0. And when energy is not equals to 0, pressure is also not equals to 0. So the graph cannot be start with 0. So this should not be the correct one. Okay. Again, here is also pressure 0. This should not be the correct one. And in this, pressure is decreasing. So it will also not right option. So the right option will be option number C. Next, in the basic band structure theory of crystalline solids, which of the following leads to energy gaps in the allowed electronic energy values? So, obviously, you know the answer. This is quite easy question. Option number A will be the correct, Bragg's reflection. This question was from Tifr 2015. I think it is easy. Question number 10. An electron makes a transition from the valence band to the conduction band in an indirect band gap semiconductor. Which of the following is not true? And this question is from Tifr 2015. What the question is saying is that an electron is making transition. It is moving from valence band to conduction band. And we are talking about indirect band gap semiconductor. There is a semiconductor, but it has an indirect band gap. So the option we can conclude by this theory. In semiconductor physics, band gap are of two types, direct and indirect. So first of all, let us know what is indirect band gap. So direct band gap is the momentum of electrons and holes is same in both conduction and valence band, and electron can emit a photon. Okay. So when we will talk about direct band gap, we will follow this one. And indirect band gap, this picture is for your indirect band gap. This is indirect band gap. It is not uniform. It like we are getting some band gap here and again an increased band gap here and again an decreased band gap here. So the band gap is not uniform. That is why it is indirect band gap. And in indirect band gap, momentum of electron and holes not the same in conduction band and valence band. So momentum is not same. So there is no momentum change. That is why option A is the right one. Yeah. Question number 11. The material inside a box is either a metal or a semiconductor. If R equals to 1 ohm is the resistance of the material, which of following experiments cannot distinguish whether it is a metal or a semiconductor? So there are 4 options and it is also an easy one. Option number B will be correct. Measurement of R using power supplies of different frequencies we can get by this experiment, like whether it is a metal or a semiconductor, because we know this from our earlier classes. This question was from Tifr 2015, and the rest questions like the paper from 2016 to 2019 I will solve in my next video lecture. So thank you for watching. Please like, subscribe and share my videos, and please share it to your friends and keep supporting. So thank you for today. Bye bye.